from the black hole is so strong that the material from the spills over. But since they are orbiting around each other, this material possesses lots of angular momentum, which is approximately at least conserved, and that's why the material, instead of falling into the black hole, starts spiraling around the black hole. Now, one of the key physics in this problem comes due to the fact that for any given, if you approximate the gravitational potential of the black hole by that of a point mass, and you neglect and you assume that the gas is sufficiently non-self-gravitating, you can work out from the balance between gravitational force and centrifugal force, you can work out a steady-state solution. And that's, for a point mass, that would be a Keplerian flow. And the key thing here is that this is a differentially rotating flow. So the angular velocity depends on the distance from the star. Now that means that you have shear, and shear crucially influences the dynamics of the system. Now, for various reasons, these disks are believed to be turbulent, having mostly to do with angular momentum transfer. You need to transfer angular momentum in order for sufficient amounts of material to accrete onto the black hole, otherwise you wouldn't be able to explain the luminosity that is observed that comes from these objects. So turbulence is, of course, a tough problem, as everybody knows, and it's bad enough if you have freely decaying turbulence and isotropic. But the fact that here it's anisotropic due to rotation and shear, it's compressible, some additional stuff doesn't help. So what many people do in order to investigate the turbulent properties of the system is to do numerical simulations. Now there are two approaches. One is to do a global disk simulations, as Vladimir does, for instance, or you can do shearing box simulations, as Anders and I do. And what you do here, you consider a tiny region somewhere in the midplane of the disk. It's rectangular. You adopt a pseudo Cartesian coordinate system, and then the good thing about this model is that the key physics are still captured, even though it's very much simplified. But the key physics, which are rotation and shear, are still captured, and the Keplerian shear is represented in the shearing box becomes a linear shear, and now that's a very convenient model both to study accretion disk both numerically and analytically, of course, as well. Right. So, and one of the problems that existed for a long time in accretion disk theory was that this Keplerian flow is linearly stable hydrodynamically. And if it's linearly stable, it doesn't seem that
is it really stable? Is it really hydrostable?
Yes. Well, at least there's no linear instability. No
pressure forces, right?
Excuse me?
That's only if you don't have the pressure forces. Because if you have, then the Grundwechsel frequency can go imagine.
Only if you change the local rotation profile drastically.
Yeah, but
I never really worked out the linear
I think
the global
the statement
stability.
for a synthesis. I guess a sync Keplerian is harder than
and Keplerian is.
Is that a more
Yeah.
simple statement or
Yeah. Well, I mean, there are disks, I think, there are lots of disks, accretion disks, that are believed to be hydrodynamically stable, as far as I know.
there's even the topological sprinkler stability.
Exactly.
Okay, but that's for Tori, and no, this is for protostellar-ish disks.
Yeah, but as I showed you this morning, like if you have a local pressure bump, then omega there can change by significant.
Right. I mean, I think if you have an obstacle somewhere in the floor, like a planet, then of course that generates lots of vorticity, and you can generate sufficient. That can generate sufficient amounts of angular momentum transfer. But whatever. I mean, okay. So actually, I don't really. What I'm going to present only assumes that the accretionist is turbulent. It doesn't matter how it actually gets there. Yeah. So what I was just saying is that they are at least stable to the Rayleigh criterion. That's a stability criterion you can work out, and it's stable. But then in the early 90s, Balbus and Hawley found that if you this flow is destabilized by the presence of weak magnetic fields, and this instability is called the magnetic rotational instability, and it's a very almost everybody seems to be working on that in accretionist physics nowadays, and they showed that in the presence of magnetic fields, the instabilities can grow on an orbital timescale, which is fast, and the system can, due to this instability, can become turbulent. Right. So, okay. So here are the Shearing-Box simulation equations. Most of you have probably seen them before. There are a couple of terms. These are just the usual MHE equations, except for the advection terms here, which are advection by the linear shear, Coriolis force here, and stretching by the linear shear as well. Stretching terms here and there.
Do you actually solve for P instead of U?
Well, I do the analytics. I do the linear theory in P. Yeah, I should have put U here. No, the code, of course, solves U. But yes, seems like a good idea. Right. So okay, and here, and this is what such Shearing-Box simulations look like with MRI turbulence. You see, well, there's a shade of blue. That's the initial weak magnetic field.
What is the dimension of the box? What is the size of the box?
Well, okay, so the size of the box is one density scale had an x in radius. This is the radial direction, vertical direction, and 4 density scale heads in the azimuthal direction.
And what's the resolution? It looks amazing.
It's 128 by 128 by 512.
So you have less, you have larger, you have elongated grid point in the azimuth.
No. The delta x, the grid spacing is the same in every. So the 4 scale has 512 grid points, 1 scale has 128 grid points.
Is it higher or is it normal?
This is normal. This is the simulation presented in Frommang and et al. 2007, 2008. Where they did the code comparison for zero-net flux simulations. Oh yes, and this is the zero-net flux simulations, which is crucial in the sense that it simplifies the theory by a bit.
You actually see some.
Yeah, you see some wiggling around. Yes, that's right. Yes, but you're going to see much more of these wiggles in the next movie. Okay. Well, first of all, these are. Many of you have seen this before. This is what everybody plots. The alpha value relates to the amount of angular momentum transport, and you can see here after 2 or 3 orbits the linear instability sets in, then so-called channel solution develops, and if the channels get too strong, so you have layers of opposing oppositely
channels with no net flux.
Well, okay, yeah, that's right. Yes, I mean it's pseudo. I mean it's locally you have channels.
Right. Okay.
Right? I mean so initially it's not channel solutions. You only get if you have a homogeneous vertical. Yeah.
But you see it at very small scales.
Yeah. Well, yeah. So you've seen this before. Yes. So but now if you look at the density field, you see this. you see, and the wiggles the small wiggles that you've seen in the magnetic field are due to these waves, these density waves that travel within the horizontal plane. The wave vector lies within the horizontal plane, which is very nice because that simplifies the theory a lot. And they seem to have a characteristic angle with respect to the azimuthal axis.
I've definitely seen this also. Is that what Stone and Gardiner?
Yeah, exactly. So actually these are also weak shocks. Maybe these are shock waves. So, and you might think, okay, these are shock nonlinear waves, so that seems like a tough problem. But fortunately, the initial excitation of these waves can be captured very well by linear theory, as I will hopefully be able to demonstrate. Yes, and it was the origin of these waves was a mystery for a while, as far as I know, and people even speculated they are numerical artifacts. Because I mean, this is a very high frequency, temporal resolution in the video. I've seen a video by Axel recently where it really looks like artifacts, really, but at a higher resolution, they seem higher time resolution may seem more physical.
Question: this only occurs in elongated boxes, right?
No, it's a square box that I have.
Yeah.
You see it even there.
Yeah.
It's probably on the web even.
Yeah, right. So they are. Okay, I'm going to show.
So some people claim it vanishes in
No.
I don't think I would be very surprised. I mean, it's true that they are. There's a favored weight number, azimuthal weight number, apparently.
Yeah.
Or at least that was, but it's not quite clear what that is. But our theory suggests that there is one.
Is it around 4 or 5?
Is
it around 4 or 5?
No, well, it depends. I mean, if you in units of it's basically a ky equal 1. It's a ky equal its largest. Usually, well, if you elongate even further and further, it might be a ky equal 2 or 3 at some point. But in these simulations, most of the powers are ky equal 1. It's the largest weight number in the system. Right, so as you have seen, these waves propagate in a horizontal plane, which is why we can average over Z and get a much clearer picture of what's going on. So you can see density, and you see these waves in velocity, certainly in radial velocity, and to some extent and also, also in. You would use the same color coding for these two, and these are weaker, but if you use the same color coding here, these would be more visible as well. So you see them in rho and density and velocity, but hardly in the magnetic field, which makes it also, of course, these two.
It doesn't show up in the magnetic field.
Well, I can go back. I mean, there are wiggles,
but
it's not really, it's not very pronounced, not nearly as pronounced as in density, for instance. So these are really hydrodynamic waves, I would say. And what you see in magnetic field are nonlinear effects.
Is it an illusion that they go back and, there's moving...
Yeah, they travel both ways, yes.
Okay.
And the fact that they are inclined, yes,
sure.
means that these are trailing waves, yes.
What? Sorry?
Trailing waves.
Okay.
So, in the shearing sheet, you have... I'm going to talk about this in a minute. But keep in mind that these are trailing waves. Right. So, and in order to learn more about these waves, it would be nice to go to, or it's very helpful to go to Fourier space. Now, doing a Fourier analysis in a shearing sheet is a bit peculiar, but can be done. So here I indicate the flow profile, the background flow, the linear shear. Yes? Now, any disturbance that has any non-axisymmetric disturbance, that is any disturbance that has a non-zero ky, will be sheared out by the linear shear, yes? And that I indicated here. So in a disturbance like that, so she acts on it, it evolves like, it will be, simply due to advection, will evolve like that. you want to allow this to happen, so to be a Batchenberg linear shear, which is why you don't use periodic boundary conditions, but rather shearing periodic boundary conditions. And the periodicity is just as, if you just follow these waveforms, you actually see the periodicity that is used for in the shearing box. I mean, you always identify points that on these lines. And all this means that the radial wave number it's not constant, but as you can see, evolves in time, and it evolves linearly in time. And the evolution is proportional to time and the estimate of the wave number. And these two, Q omega is constant, so the evolution of a single Fourier mode you can picture as starting in the leading phase at infinite kx, such that kx over ky is minus infinity. Then the mode is affected by the linear shear, kx decreases or increases, I mean, it goes from minus infinity towards 0, then swings, and that is called the leading phase. Then it swings through 0, the radial wave number becomes 0, and then it increases again and goes off to kx over ky to plus infinity. And that's called the trailing phase. So this is leading, swings through 0, and now it's in the trailing phase. And as you've seen in the films before, these waves are trailing. So what happens is, apparently happens, is that these waves are excited as they swing from leading to trailing. The excitation occurs when they at the swing stage. Okay, so right, and you can do the Fourier analysis. Yes, and this is a bit of a confusing plot. I mean, I tried to plot the power spectrum of these, so this is just the amplitude squared of this thing, and you can see that there's shear in k-space. Yes, the wave numbers are time dependent. Yeah, so it looks a bit funny, but you can see that most of the power is on this line. So you see that. So you see that the volts come in, yes, and the color coding is obviously the amplitude, and then they gain amplitude and at this stage. So most of the power is in this region. Yeah? Ky equal 1 and lowish kx.
So that's for perturbational density?
Yeah.
Okay.
Yeah, that's
But
right.
why do you only have positive kx here?
Yeah, because I'm just, because of the reality condition, this is there and this is there, so I only need to plot the half space.
Yeah.
This is stupid, especially in the next plot.
Can you not identify a trailing and a leading wave on that plot?
This is trailing, this is leading.
I see, okay.
Yeah. So you see that there's nothing in the leading phase and everything is in the trailing. Right, okay, and so these here show cuts through along kx, along the x-axis, yes? So this plot is simply a cut through here, and this plot is a cut through 0. And here it's especially stupid that I not plotted this part, but you would see that the modes come in do almost nothing, then swing through 0, and then get excited. Yeah. You see these bouncing motion, yeah? Which looks funny as well.
I don't understand here, what is this flashing?
That's the power. I mean, the power is not, the power is, it oscillates.
Okay, I see.
Yeah, so which you also see here. This is why it flashes, yeah, the color coding.
Tobi, I don't understand your point with kx. It doesn't leading to trailing implies going from negative kx to positive kx?
Oh, yeah, from negative kx over ky to positive kx over ky.
Yeah. So when I see something coming from the left side, it means that they're just turning from
Leading to trailing. This is I just got the lead trailing stage.
But we're not seeing leading waves.
We're not seeing leading, no. But I have a next plot which is much nicer anyway than these videos, and there you can clearly see. Well, I didn't expect that slide. Maybe I should just directly skip here. So this is what you can record every single wave. You can record in the simulation. You can record the evolution of a Fourier amplitude with radial wave number. which is a very nice tool for analysis, I think. And this is how it looks like. So this is the amplitude. This is I think should have put a title here. This is probably the imaginary part of Py, the Fourier amplitude of the y component of linear momentum. And you see that there's, evolves very aperiodically, I don't know, in the leading phase. There are no oscillations in the leading phase. And it swings through zero and then suddenly gets excited. This is how they typically look like, the evolution of wave amplitudes.
Yeah, so it's very excited around kx of
Yeah,
0.
the excitation clearly occurs around kx equals 0.
And what's about the real part of
Well, that looks similar.
the signal?
Yeah, I just chose to plot the imaginary parts because I think it's a larger excitation. But it always looks like this.
So why is it? But why is it?
Yeah.
Yes. But why is it? Why did you actually plot Py and not Px or rho?
This is Py. Well, I plot Py because so what you want to do is you want to, in order to come up with an analytical theory of this, you want to write down a wave equation. Yeah?
Yes.
Now, we integrated over that, and we went into Fourier space. So then the equations look like this. Yeah. In terms of, and here where it becomes easier to work with momentum instead of velocity. And because the nonlinear terms are, there's no sort of, the density, the continuity equation is linear all of a sudden, which is nice. and there are then these nonlinear sources, just the turbulent stresses, nonlinear stresses on the right hand side of the momentum equation. Yeah? And if you massage these equations a little bit, you arrive at a wave equation for Py. You can also write down wave equations for rho and Px. They're a little more complicated.
What is this?
So,
The n thing, n, x, and y.
those stand for nonlinear. This is the dx.
Nonlinear are also big things.
The divergence of the nonlinear stress tensor.
So we would normally start by setting it to be 0 even and see.
Yeah, so
Because I mean, it's all about it.
so n is div t and tij is bi bj. Yes, all the nonlinearity, all the nonlinearity.
It's the lowest force.
Hmm?
It's the lowest force.
And the Reynolds stresses, Maxwell stresses. Yeah.
Oh, you had a new idea. So, okay, it's a combination of advection and lowest force. So the two nonlinear.
It's like the equation for acoustic.
Exactly. Yeah. So the whole theory is sort of in the spirit of Leibniz's classic theory.
So we will use AC equal to 0.
KZ is equal to 0.
But if it is excited near kx equal to 0, what does it actually mean? Like large scale or?
Kx 0 is
No variation.
infinitely large scale in the radial direction.
So it's a wave plan.
Well, that's what's happening.
If the waves start like that, in a minute it's like this, and with no radial variation, then it's amplified.
Yeah, exactly.
And
And
then
it's a flat thing then, right?
And then it becomes trading, and it has this oscillation.
That's what's going on.
So why is there a time difference of n y? The right hand side?
Well, that just comes out if because you take the second derivative of this equation.
Oh, I see.
D squared Py, D and y t.
Yeah.
Okay, so you have a time dependent harmonic oscillator on the left hand side, and you have source terms on the right hand side. And the idea is now that these source terms are switched on, or are crucial, at kx equals 0. Yeah? Okay. So, and there are two types of source terms. There's these nonlinear stresses, and it's shown that it's actually linear. And that's what we call the potential vorticity. I'm never quite sure whether this is really, it's certainly similar to the potential vorticity. And this term, I haven't written this down, but the potential vorticity in turn, if you write down the evolution equation for that quantity, varies only due to nonlinear stresses. It's conserved at linear order, which is why previous papers that have worked on this always set this term to 0 as well when they did a linear analysis. But this term is actually crucial. This is the crucial term. As far as the excitation is concerned, you can forget about the nonlinear terms, fortunately, as I will show you on the next slide, I think. Yes? So you've seen showed you this plot before. Here's the weight equation. Now, in order to reproduce this, the very first approximation one can do is simply cross out the second time derivative. Of course, you won't get any waves in that case if you do that, but still, you can see what that looks like. And to forget about the nonlinear terms for simplification. Yeah? If you do that, you get a curve like this, the blue one. So you see that there's a very good match in the leading phase where there are no waves, and in the trailing phase, the mill oscillates around this solution, and we call this the balanced solution. Yeah?
The what?
The balanced solution, or background solution, or something like that.
So this is a pure density wave, or is that what you call this? Is that density wave?
I would call it inertial acoustic wave.
Inertial acoustic wave.
I think that's Rossby wave actually.
No, it's not a Rossby wave.
Well, it looks like one.
No,
I don't know.
You would need some kind of pressure.
Well, Rossby waves are sort of atmospheric lines.
Well, no, yeah, like it's called like that because it comes from atmospheric.
But it certainly is an inertial acoustic wave.
Yes, that's inertial wave because Rossby
it
has a two-dimensional flow. That's like the atmospheric layer.
So
That's Rossby wave.
acoustic, inertial.
Inertial waves. That's inertial acoustic.
Yeah. Right.
So it's like the difference between alpha band waves and like a magnetosonic wave.
No, with this background state, you cannot excite Rossby waves.
No, because even if you have magneto-acoustic wave, you have a...
Okay, let's.
Rossby really requires variation in the latitude, so to speak.
That's what it says on Wikipedia as well.
Wikipedia, exactly, you know.
That's
latitude, you know, like it means the, well, like, it's where the shear comes from, right?
What you need for the Rossby
I
wave.
mean, this, you know, the omega there gives shear.
I would claim for Rossby wave, you need some kind of balance between, you need some kind of geologic balance between pressure and and protocol, and this you don't have.
Oh, okay, right. Okay, let's can we continue the cycle?
Okay, sure. Sorry.
But Tobi, one question. So you, what is your you start at some initial condition at kx of minus 6 pi.
No, this is from the simulation. The black curve is from the simulation.
What about this blue curve?
The blue curve is just, I don't need an initial condition. I mean, well, okay, for the blue curve, I take the source term from the simulation. That's right, I should have mentioned that. And then the blue curve is just that thing taken from the simulation divided by the inertial acoustic frequency. Yeah. But that gives you already an idea of the important, I mean, that hints that this term is sort of crucial compared to the other nonlinear source terms. Yeah. So what does my next slide say? Yes, okay, so to further simplify this model, and to further simplify matters, if I had plotted the potential vorticity, you would have seen that this is a very slowly evolving quantity. There are no waves in that quantity. It sort of goes up around zero, but it varies slowly. So to first approximate, we can say, okay, let's take this to be constant. Yeah? Potential vorticity. There's still kx of t, which is time dependent, but let's take this thing to be constant. And then, if you dimensionalize the equations and in terms of these quantities, dimensions, time is typically kx times 8 times the scale height, and we have this epsilon parameter, which is ky times the scale height, and then the equation looks like this. So this equation you get by throwing away nonlinear source terms and assuming that the potential vorticity is constant. Then you arrive at this equation. And I call this parameter epsilon because we're going to use the fact that this is actually small in the long wavelength limit. Yeah? And as you saw in the simulation, these waves are at ky, a long wavelength, yes, compared to the density scale height. So we are on a limit, or we can go on a limit where epsilon, where this parameter is small. It's not much smaller than 1, as I indicated here, but formally we can assume it to be. Right, and then and now this equation you can integrate on the computer. Yeah. I mean, this is just a toy equation to motivate the analytic theory that is behind this. So this you can integrate on a computer. I've done this with Mathematica, which is very nice for that purpose. I didn't know that before I did that. And it looks like the black hole. This is what you get on a computer. Which is surprising, because, I mean, this looks like a very innocent equation, but still, if you integrate it on a computer, you reproduce exactly the same behavior as observed in a simulation. Yeah? And now, again, we have the slowly varying solution, which is simply if you cross out the double time derivative, which is this y equals tau over tau squared plus 1, and then I chose some arbitrary value for the small parameter, and then, again, in the leading phase, so tau is negative now means it's leading, tau is positive, it's trailing again, and you see the qualitatively the same behavior. It matches very well in the leading phase, and then it oscillates around the slowly varying solution in the trailing phase. Okay.
So if you have different epsilons, what happens?
If you make epsilon even smaller, I'll show you what the dependence on epsilon is in a minute. Right, okay, so, but now we want to capture the wave part of the solution. Yeah? So, for this, you have to do, or what you can do is use WKB theory, yeah? As you saw here, we have a small parameter, and if you do perturbation, you need to use. So you write the equations as a solution to the inhomogeneous problem, as everybody knows, a particular solution to the inhomogeneous problem, and a general solution to the homogeneous problem. Yeah? Now, the particular solution to the inhomogeneous problem we take as the blue curve. Yeah? And then on top of that, we add a standard WKB solution to the homogeneous problem. Now, WKB is applicable because a small parameter multiplies the highest derivative, so we have to do singular perturbation theory. And now this is what you have to do is do an asymptotic matching exercise. Yeah, you have to write down an outer solution valid. So okay, so you have
to be cool.
You
have to be cool.
Well, okay. So this is actually not. I mean, asymptotic matching procedures are standard. Yeah, you can read books on that and everything. They are annoying to do, but standard. What this makes this is a little less standard because usually if you have if you deal with turning points, they rely on the real axis. Yeah? And that's you get area equations. You get area equations here as well, but here. Nothing goes on the real axis. Nothing becomes singular. In fact, if I were to look at that equation and didn't know what's going on, I would never expect that there's actually something happening at tau equals 0, because there's nothing. Yeah, if this thing were to become 0 at some point, yeah, one could think that the sort of balance breaks down and something dramatic happens. But this never happens. It never becomes 0. But it does have turning points in the complex plane. And it turns out in order to derive a wave amplitude for these waves, you have to do a turning point analysis in the complex plane. You have to do an asymptotic matching procedure in the complex plane, which is a bit of a pain. But can be done. And how to do this was shown by these two guys. And so essentially what you do is you deform your real integration from the real axis onto lines of stationary phase, or steepest descent, or they have many names, and you go close to the turning point, you write down a solution that is a homogeneous solution that is valid far away from the turning point, you write down an area type solution near the turning point in the complex plane, and you match those two together, and what that gives you is the wave amplitude of these waves. And so the resulting equation is this. This is the solution you get. You see there's the inhomogeneous solution plus the WKB solution. This is just the standard. This is just the standard WKB expression, that many of you will recognize, I'm sure. and you have the wave amplitudes, and those can be computed by this matching procedure, and they are expressed in terms of the small parameter and look like this. The dependence looks like this, and you see that it's exponentially small in the small parameter, which means that if you go to very small parameter, there's nothing. Yes? So there is some optimal wave number for which this thing is maximum. But then again, in real life, this thing is multiplied by the potential vorticity, and you need to look at the spectrum of potential vorticity as a function of ky, and so we are not extremely sure about how that actually looks like.
You said epsilon equal to 0, then basically the turning point goes to complex infinity, right?
In effect, perhaps, but formally, I don't, well,
epsilon gets larger, the turning point gets closer to the real axis.
if you, when does it get closer?
As your epsilon gets larger.
Well, effectively, I guess, maybe, but I mean, if you look at this, the turning point is always at tau equals plus minus I.
Right, sorry.
No matter what epsilon is. Yeah. Okay, and so here's the comparison. The black and blue curve I've shown you before. Black is numerical integration, blue is the slowly varying solution, and red is the full WKB solution, slowly varying solution plus WKB green. And you see that there's an extremely good match between these two curves. Yeah.
Would there be a mirror symmetric solution as well that is somehow not excited by the initial conditions?
Yeah, well, yes, so this solution extends actually here. It's actually, yeah, it's point symmetric because around this point, this solution. But you set the amplitudes to 0, I mean, this is like setting the amplitudes to 0 for negative time.
But there is no solution that would start out oscillating and then would end then?
No. I don't think so.
He hasn't kept the oscillation yet in the solution.
Well, then what is this?
Well, I mean, you do in the asymptotic analysis, you impose this. You say, before you even do the analysis, you say, okay, I have no waves at negative time, and I want to compute the wave amplitude for positive time. So if you formulate the problem differently, you can get, so you're right, you
What's
can.
the red line?
The red line is this thing. The red line is the analytic solution from the WKB analysis. And the black line, which you hardly see, you only see it here around 0, because here the blue line is a very good match, and here the red line is a very good match. So, yes.
So what was in the black line?
The black line is the numerical integration of this equation. If you solve this with, if you solve this with mathematical or any ODE solver, and you start at t equal minus 100. And you initialize, yeah.
And so the black line is even very close to the numerical solution of the turbulent simulation.
Exactly, yeah. I will show you in a minute that that's very true.
So basically on the right, the red and the black line are the same.
Yeah, they're all plotted. Yeah, you don't see it. Yeah, you see here the black line, and then here they're already identical.
Technically, if you were to make this a dashed line, the dashed red line,
Yeah.
both.
Right. Okay. So then. Okay. And here's the. So what you can do now is to compare with the output from the simulation, from the Fourier amplitudes that are recorded during the simulation, and you record the potential vorticity at the swing stage at k is equal to 0. That's the only thing we need. And then you can compute the WKB solution that I just showed you, and you see that even in the fully nonlinear, turbulent, three-dimensional simulation, the initial excitation is very well matches very well with the predicted curve. The amplitude is pretty.
This figure is just for one.
This is for one shearing wave. Yes.
Just for one snapshot during the simulation.
No, it's for one shearing wave. So what I do is I write down these two-dimensional Z averages. I do a Fourier analysis of this, and I look at the modes, and then I record the amplitude for each Z average. I write down I focus on the single mode, and I write down the amplitude, and I look at the next one. And as time increases, kx increases, and the amplitude of the, and so I can plotted time series of the.
So it's actually 60 times then?
Yeah. Well, yeah, it's kx, but kx is linearly proportional to time. Yeah. Right. So yeah, so at least for ky, and this is of course wrong. This should be 1 and 2, not 2 pi and 4 pi. So, so you see that initially there's a very good match between theory and simulation. It gets worse for higher kx. Now, that's obviously due to nonlinear effects that cannot be captured by linear theory.
And you haven't included any nonlinear effect yet?
In the analysis, no. So I'm trying to investigate. So the next project would be to investigate what this nonlinear damping is about. As a first hint, well, our first thought, which is probably wrong, was that maybe turbulence just acts as diffusion. So what we simply did is to take the wave amplitude we computed and multiply it with e to the minus nu integral over kx squared dt, yeah, and then figure out empirically what the value for nu is. Now, what's interesting is that if you take, this is alpha again, it's around 0.01, 0.005, something in between. If you take 0.005, which is indicated by the blue line, then, and you do this, then you get a very, very good match between simulation and...
Why did you say it wasn't so good?
Well, because I think I received some criticism for this suggestion that might be the effect of, and it makes sense to me because, I mean, turbulent diffusion, I guess, works when you consider the effect of high oscillatory turbulent fluctuations on a more slowly varying mean flow.
That's correct, yes.
But here's the opposite situation. I mean, if anything, these waves travel at the speed of their sound waves. They oscillate. The characteristic timescale of these waves is much faster.
Yeah, the timescale, yes, but not the wave length.
It becomes, I mean, as it springs, it's very long wavelength, but as it's being trailed, it becomes very short wavelength.
Right.
In the end, right? So I think just as you're swinging, you could probably consider that some kind of turbulent diffusion.
Yeah, maybe, but right.
Okay,
maybe it's not a coincidence that this matches so well.
But in the sense that ky is equal to 1.
Yeah, but after kx gets enormously high. Right? At the end here, the kx is very high.
Well, yeah, it's not. Well, not. I mean,
not that high.
It's kx.
Well, your
Nyquist,
I guess your Nyquist.
Or
Okay, so one would be the largest scale of the bar.
the Nyquist frequency is here. Maybe no further. But but the thing also is that, as you saw earlier in the plot of the density fields, these are shock waves. If you plot one-dimensional cuts in real space, they're clearly shock waves. So my guess is actually that this is just some shock phenomenon. But as I said, I will...
So how does this compare to the shock diffusivity that you have in the code?
To what?
He doesn't have a shock viscosity.
No, I don't use...
The molecular viscosity, how does that compare to that?
Right. Yeah, I'm sorry. Yeah, this is an order of magnitude larger than the molecular viscosity.
10 times.
And because, what is the value of the
the value is the Reynolds number is so RE equal to omega h squared over nu, yes, is 3,002. Strange number.
3,000 something.
Yeah. So, well, these things are 1, so nu is 1 over 3,001. I mean, the units are. Yeah. And the magnetic frontal number, Reynolds number, is 4 times higher, so that the frontal number is 4. These are this is the parameters that Fermat and Papalozzi use, which I just adopted.
And what is the size of the box compared to what is the typical length scale of the box?
It's a density scale height.
It's a density scale.
Yeah, it's H. Yeah.
H. Okay, so and what is the extension in vertical, horizontal?
It's H in radius, H in vertical, in the vertical direction, and 4H in the shear board in the asymmetrical direction.
So you actually have vertical stratification?
No.
No. So why do you talk about scale height then?
Well, it's just that's what people talk about. It's not, obviously, it's not really scale.
And the coupling between the inertia, so the time scale of the athletic wave is the same of them than the Coriolis one, right?
Yeah.
So no, that's
Well,
there's really no scale height. G is equal to 0. And scalar would be G divided by C squared.
yeah.
C squared
So
divided by G.
right. So H. Okay. But people call it scale height. But yeah. So H is simply. But there is a sound speed, right? There's a well-defined sound speed.
Yes.
And there's a well-defined angular frequency. So H is simply C over omega.
I don't see a problem in calling that scalar.
Yeah.
See, that's what it is. If you has certification.
What?
It is a scale height if you has certification. And I still think it's a characteristic length scale.
Yeah, of course.
Yeah.
Yes, and then in your setup, H is around 1.
Yeah, it is one. It's
That's one.
one.
Okay, so
Because I
that-
mean, there are also
coupling
using
is maximum
units of the
between-
speed of sound. And
What will be interesting maybe to rescale your equation such that you have a faster acoustic wave compared to inertial wave, for example. Just to excite the initial spectrum and not the acoustic one at the same time. But in this case, the coupling is optimum between the two. Because the sound speed, the time that you derive from the sound speed, it's of same order than the Coriolis time, 1/2 omega, which is the characteristic time scale of inertial wave.
right.
Then your setup is exactly done for inertial acoustic wave.
We change to in effect change the value of omega. Yes. Well, I guess you start now.
And Tobi, did you try to extend the radio side of the box?
Yeah.
Like 2, and you have the same kind of
Yeah. So in this, if you have one scale that is in the radio direction, you see basically one wave. If you look at it in real space at any given time, so one wavelength. If you have 2, you see 2 wavelengths.
The trick is crazy in this one. And finally, you just multiply the amplitude by some.
Yeah.
And what is true is that you take into account the temporal variation of k in the exponential.
Yeah, but this is just empirical modeling.
Yeah.
Yeah, but it works so incredibly well that there must be something to it.
You know.
Did you estimate what the turbulent viscosity would be based on velocity fluctuation?
No, only based on, as I said, based on alpha. So if I take the Shikura-Sunyara alpha viscosity.
So then, okay, so in other words,
Well, it matters, it's sort of.
nu is alpha times C times your H.
Yeah, C and H are 1, so it's the blue line.
And alpha is 0.01 or 0.06.
So it's the same order of magnitude as the alpha viscosity. So. Okay, yeah. And so maybe as a last comment, you may be wondering why this is, why these waves are actually worth studying. There's been a suggestion. I think there may be a couple of reasons, but also there has been a suggestion by Nelson et al. Recently that these waves actually may have a profound effect on planet migration, because the gravitational potential may interact with planets, and and provides stochastic forcing on the planet and
like one other thing more that they can do, like is if they merge, they have so much vorticity that they can lead to vortices also. It's an interesting thing, I see it. There's a wave is happening also in my models, but I call them rescue waves. And yeah, I mean they lead to vortices. If you can trap them, like within some pressure maximum, right? So then the modes grow there. I'm not sure that is the same wave though, but which other wave comes, like when you have shear and
yeah, so I should have said that. I mean, exactly. So these waves are also observed in global simulations, and there's reason to believe that.
I also see them in my simulation.
Yeah. Right.
And they travel in global simulations always outwards?
No, both ways. I think.
Because in your case, of course, in and out is undistinguishable.
Yeah.
And do you see that there's a wave can participate to the nominal saturation of the MRI?
I don't think it has. I don't think they have they actually play an important any effect there, any appreciable effect as far as MRI is sustaining the MRI is concerned, or transporting angular momentum. In fact, they don't. Yeah, but they do. They're trailing waves, so they transport angular momentum outwards. Yeah, in the right direction. But
they can be quite important in the dead zone where you don't have the MRI.
Right.
I mean, they can drive the transport through the dead zone.
Mm. Yeah.
Have you seen that?
Sorry?
You could maybe see such a thing. Have you seen that?
Yeah.
That it goes through the dead zone, yeah?
Yeah. Yeah, I mean, like I showed it on this morning, but like no one cared.
And so that means these guys are excited. How do you excite the leading waves? Have you any idea about that? Do you need to excite leading waves all the time? Can the trailing wave self-excite itself to a leading wave or
Non-linearly.
yeah, exactly. It has to be non-linear, of course.
I don't know.
But it would be interesting. There was some claim about hydrodynamical about swinging waves that as they become trailing, that they by some non-linear interaction they can spawn another leading wave.
Right.
So I think this is quite interesting.
But I mean, can't you have any sort of representation, and then if it has a component that corresponds to the wave, then when it swings, it gets amplified and that's the oscillation. I mean, you have like gravity waves, what is called in galaxies, density waves in galaxies, basically.
I mean, if you have that, you can transport angular momentum without MRI. Then you just have one leading wave, and it will keep self-exciting itself.
It would completely change the story because you would not depend on fluctuations, but you would have constant motor.
But it seems a little bit like putting yourself up. So it's too good to be true that if waves could ever do that, but who knows? It's a non-linear effect. So,
Okay.
Thanks, Tobi. So actually, you have to leave around 4, right?
Mm-hmm.
So do you want to?